Welcome to Electronic Seed YouTube channel. Today in this video we will learn about routing in VLSI. Let's get started. Routing is the step where your circuit takes a real, manufacturable shape on silicon. It comes after floor planning, placement, and clock tree synthesis. The router connects every logic cell macro and I/O pin according to the netlist. It does this using a precise network of metal wires built on multiple layers. Good routing keeps wire length minimal, which is great for performance. It also reduces signal delays, helping your chip run faster. And it maintains manageable congestion, so wires don't crowd each other. Poor routing, on the other hand, can introduce short circuits between wires. It causes electromagnetic interference, or EMI, which messes up nearby signals. Poor routing also creates timing violations, meaning signals arrive too late. In the worst case, it can render the entire chip non-functional. Every stage in the VLSI flow builds directly on the previous one. Floor planning establishes where the large macros are placed. Placement, then, sets the exact coordinates for all standard cells. Clock tree synthesis distributes the clock and reset signals. Finally, routing completes the physical design flow by adding all the wires. A clean layout achieves minimal wire length. It also delivers reduced signal delays. And it keeps congestion manageable. A dirty layout, however, leads to short circuits. It also causes EMI and crosstalk between signals. And it makes timing violations emerge, hurting performance. Routing doesn't just affect performance, it determines whether the chip can be manufactured at all. The router must satisfy all of the foundry's design rules. This requires placing every piece of metal geometry with precise coordinates. Good routing directly impacts yield and reliability, which are crucial for production. If routing is poor, the chip may simply be impossible to manufacture. Fixing it later requires costly design respins, which can run into millions of dollars. Those respins also delay your time to market significantly. Clean routing, in contrast, enables successful tape-out. Getting routing right is absolutely essential for commercial viability. Routing is the physical design step where we draw the actual metal wires. It connects the pins of cells macros and I/O ports. The router follows the connections described in the Post-CTS netlist. It uses routing grids that are defined in the Process Design Kit, or PDK. And every wire must satisfy all of the foundry's design rule-checking constraints. Phase 1 is called global routing. It divides the chip into routing regions known as global cells or G cells. The router assigns nets to paths that pass through these regions. At this stage, there is no commitment to exact wire geometry. Phase 2 is detail routing. Here the router assigns actual metal tracks and places vias. It then resolves design rule violations iteratively. Detail routing finalizes the complete physical layout. Routing simply cannot begin without the prior physical design stages. Each stage provides critical information that the router needs. Floor planning gives die area, macro placement, and pin locations. Placement supplies the exact coordinates of every standard cell. And clock tree synthesis provides pre-routed clock and reset paths. The router must know the exact location of every cell and every pin. Clock and reset nets get special priority during routing. Pre-routing those critical nets preserves signal integrity. Timing constraints also guide how the clock tree is routed. After that, the remaining tracks are allocated to data nets. The Post-CTS netlist describes all the logical connections that need to be made. Those connections must be physically realized as metal wires. The netlist specifies exactly which pins need to be connected together. It also defines fan-out and the load that each driver must handle. DEF stands for Design Exchange Format. It contains the positions and orientations of all cells. DEF also defines the die boundary. LEF stands for Library Exchange Format. It describes the abstract views of each cell in the library. LEF includes the geometries of all the pins, and it defines the routing layer rules for the technology. SDC stands for Synopses Design Constraints. These timing constraints guide the router's decisions. SDC defines clock periods, input delays, and timing exceptions. The technology file, or PDK data, is also required. It includes definitions for each metal layer. VIA rules and spacing constraints are defined here too, and it specifies the minimum width rules per layer. Congestion is one of the most critical challenges in routing. It happens when the number of nets exceeds the available metal tracks. Congestion occurs in specific routing regions, not uniformly across the chip. It prevents the router from legally completing all wires. Imagine we have 3 blocks, a memory controller, an ALU, and a peripheral interface. These blocks are placed right next to each other. The netlist requires 40 signal connections between them. Many of those signals need to cross the boundary between memory controller and ALU. But only 30 routing tracks are available in that region. The result is congestion overflow. You cannot complete all connections without causing spacing violations. Unresolved congestion leads to short circuits between adjacent wires. It also increases EMI and crosstalk between signals. DRC violations will block your tape-out completely. The router may try longer detour routes, but that makes things worse. Increased wire length then degrades timing significantly. One strategy is to spread cell placement out to open up more routing channels. You can also insert routing blockages over macros to keep wires away. Using higher metal layers for long routes helps reduce congestion in lower layers. If congestion is severe, you may need to refloorplan the macro placement. And always analyze congestion maps iteratively throughout the flow. Routing is not just about making connections. It's about making optimal connections. You want to minimize total wire length. You also want to minimize the number of vias. Reducing congestion distribution is another key goal. All of this must be done while meeting timing constraints. And you must satisfy every single design rule. Shorter wires directly reduce RC delay. This leads to lower propagation time for signals. And that improves the maximum operating frequency of your chip. Here's the wire delay equation. Delay is proportional to length L. So minimizing L is a core objective of routing. Each via adds resistance to the signal path. Fewer vias improve signal integrity. Vias create impedance discontinuities that can reflect signals. Multiple vias also increase manufacturing cost. So via minimization is an important design goal. Nets on the critical path need priority during routing. We allocate dedicated routing resources to those critical nets. Shielding helps protect sensitive signals from noise. Clock nets get special handling to minimize skew. Reset distribution also requires careful attention. Spacing rules from the PDK are mandatory. Minimum width rules apply to every metal layer. Vias must satisfy enclosure rules for each layer. All of these rules must be satisfied without exception. This is necessary for a manufacturable chip. The main output is a rooted DEF file. It contains a geometric description of every wire. The location of every via is specified. All metal shapes are defined in detail. This is the final physical layout representation, ready for sign-off. After routing, we perform Design Rule Check, or DRC. DRC verifies that all foundry spacing rules are met. It also checks width and enclosure rules. Your chip must pass DRC for tapeout. LVS stands for Layout versus Schematic. It confirms that the routed layout matches the original netlist. We then extract parasitic RC values from the geometry. Finally, static timing analysis validates timing with those parasitics included. Step 1. Load the Post-CTS netlist in DEF file. Step 2. Import everything into a physical design tool. Common tools are Innovis or Fusion Compiler. Step 3. Set your routing constraints. Define which nets have higher priority. Specify any shielding requirements for sensitive signals. And set the layer usage rules, like which layers to avoid. Step 4. Run global routing. Then analyze the congestion maps that the tool produces. If congestion is bad, adjust placement and rerun. Step 5. Run detail routing. The tool will resolve DRC violations iteratively. Step 6. Run post-route optimization to clean things up. Step 7. Fix any remaining timing violations. Reduce crosstalk effects by adjusting spacing or shielding. Repair any DRC violations that still exist. Then extract parasitics into SBEF format. Generate RC models directly from the final geometry. Run final static timing analysis for timing closure. Run DRC and LVS sign-off checks one last time. Finally, prepare the layout for tapeout. Routing complexity grows exponentially as we scale below 5 nanometers. More metal layers are required to handle all the connections. Routing grids become much denser, making congestion worse. Design rule constraints multiply at advanced nodes. Traditional routing methods are no longer sufficient. AI-assisted routing engines are now emerging. Machine learning-based congestion prediction is becoming standard. Modern EDA flows are incorporating AI more and more. But the fundamentals of routing remain essential to understand. Congestion, wire length, and layer management are still key. These principles stay the same even as technology scales.